Imagine standing on a tiny, rocky island in a vast, dark ocean, where the waves are made of gravity and time. We call this island Earth, and for most of our history, we believed we understood the giant neighbors circling us in the dark. But as our robotic eyes travel deeper into the void, we are finding that our textbooks might have been telling us a fairy tale. Jupiter, the king of our solar system, has long been described as a simple, gargantuan ball of colorful, swirling wind and gas. We were taught that it was a fluffy giant, a failed star that never quite gathered enough mass to ignite its own nuclear fire. Yet, the deeper we look past those iconic marbled clouds, the more we realize that Jupiter is not a gas giant at all. It is a world of liquid metal, a place where the laws of physics are squeezed into shapes that defy our earthly intuition. To understand Jupiter is to confront a scale of existence so massive that it challenges our very definition of what a planet is. This titan is heavier than every other planet, moon, and asteroid in our solar system combined, a true gravity master of its domain. If Earth were the size of a single grape, Jupiter would be a massive basketball looming over our tiny world with silent, crushing authority. For centuries, we could only watch from afar, sketching its great red spot and counting the moons that dance in its powerful wake. Our first real glimpse of the truth began in 1974, when Pioneer 11 captured a grain of the giant's true, terrifyingly beautiful face. Then came Voyager, 1 inch 1979, providing us with a haunting time-lapse of a world that seemed to be constantly breathing and churning. These images were masterpieces of early science, but they were also a veil, hiding a core that shouldn't exist according to our theories. Most scientists assumed that beneath the clouds lay a solid, rocky heart, a massive anchor that caught the gas of the early nebula. This core accretion theory suggests that Jupiter grew by smashing rocks together until it was big enough to start vacuuming up the universe. But there is a second, more chaotic possibility, that Jupiter was born directly from a collapsing cloud of gas, much like a lonely star. If this were true, the giant would have no solid heart at all, existing instead as a seamless, layered cake of ancient, compressed stardust. For decades, these two ideas battled in the halls of academia, each side waiting for a sign from the giant itself to settle the score. That sign arrived in the summer of 1995, in the form of a cosmic intruder that would literally tear the planet's secrets wide open. This was comet Shoemaker-Levy 9, a frozen mountain of ice and rock that the universe decided to throw at Jupiter. As it approached, the planet's immense gravity didn't just pull the comet in, it reached out and shredded it. The comet was torn into 21 distinct fragments, resembling a string of pearls hurtling toward a violent end. Humanity watched with bated breath, but there was a catch. The impact was set to happen on Jupiter's far side. By a stroke of cosmic luck, the Galileo spacecraft was already in position, acting as our lone witness in the dark. It captured the largest explosion ever recorded by human eyes, the energy of 300 million atomic bombs unleashed at once. When Jupiter rotated, we saw the scars, massive black plumes of debris rising thousands of kilometers into the sky. For the first time, Jupiter had been poked and its internal guts were splattered across the upper atmosphere for us to see. Galileo flew through this debris and found something startling: water, vast amounts of it lingering where it shouldn't have been. This discovery shattered our old models and forced us to send a new specialized detective to the giant, the Juno probe. Juno wasn't interested in the clouds, it was designed to peer through the gas and map the planet's heavy gravity. What Juno found was that everything we thought we knew about Jupiter's interior was, quite frankly, a little bit wrong. To understand why, we have to start at the top, where the temperature is a freezing -100 degrees Celsius. Here, ammonia acts as a natural antifreeze, allowing liquid water to exist alongside ice crystals in a chaotic, frozen soup. These mixtures create mushballs, slushy hailstones that fall deep into the atmosphere, carrying ammonia and water away from the surface. This process fuels lightning storms so powerful they would dwarf any hurricane ever recorded in the history of our world. These storms are anchored by the Great Red Spot, a vortex so deep it reaches hundreds of kilometers into the abyss. But as we descend deeper, the cold vanishes, replaced by a heat so intense it could melt the strongest alloys. This heat isn't from a fire, it's the result of pressure the weight of a world's worth of gas squeezing inward. At this depth, the hydrogen gas begins to change, losing its identity as a gas and becoming something far stranger. As we dive deeper, the familiar boundaries of chemistry begin to melt away under the sheer weight of the giant. At about 1,000 kilometers down, the hydrogen gas is crushed so tightly that it turns into a liquid. This is the true surface of Jupiter, a vast, globe-spanning ocean of liquid hydrogen, the largest in our solar system. On Earth, hydrogen only becomes liquid at extreme cold. But here, the pressure is so high, it stays liquid while boiling hot. This ocean is 20,000 kilometers deep, an abyss so profound it makes our own Pacific look like a shallow puddle. But the journey isn't over. As we sink further into the darkness, the pressure reaches millions of times that of Earth. At this depth, the hydrogen molecules are squeezed so hard that their very structure collapses in on itself. The electrons, usually tethered to their atoms, are forced out, flowing freely through the dense, hot liquid like a river. This is metallic hydrogen, a state of matter so exotic it barely exists anywhere else in our entire neighborhood. It isn't solid like a piece of iron, but it conducts electricity with the same terrifying efficiency as a power line. As Jupiter spins, this massive sea of liquid metal swashes around, creating a gargantuan, invisible magnetic shield. This magnetic field is the largest structure in the solar system, a silent ghost stretching millions of miles into space. If we could see it with our eyes, it would appear several times larger than the moon in our night sky. For a long time, we believed that at the bottom of this metallic sea sat a solid rocky prize, the core. We imagined a dense ball of iron and rock, perhaps 10 times the mass of Earth, acting as the planet's skeleton. But when the Juno spacecraft measured the gravity of the deep interior, it didn't find a solid wall of rock. Instead, it found what scientists call a fuzzy core, a strange, blurry region where the center has begun to dissolve. Imagine a spoonful of sugar half melted in a cup of tea. That is the heart of the king of planets. The heavy rocks and metals aren't a solid ball, they are mixed into the metallic hydrogen in a chaotic, soupy mess. This discovery sent shockwaves through the scientific community, because a core like this shouldn't stay fuzzy for long. The mystery of the fuzzy core suggests that something monumental happened in the early days of our solar system. If Jupiter had a solid core to begin with, physics dictates that it should have remained a distinct, heavy anchor. However, a new theory posits that Jupiter was once the victim of a truly gargantuan, head-on planetary collision. This wasn't just a stray asteroid, it was likely a super-Earth, a rocky planet 10 times more massive than our own. Imagine two titans of the early nebula smashing together at speeds that would make a bullet seem stationary. Such an impact would have been powerful enough to shatter Jupiter's original core, scattering its fragments into the surrounding hydrogen. This cosmic trauma would have stirred the planet's insides into the diluted, soupy state that we observe today with Juno. Recent computer simulations have tested this great impact theory, and the results are surprisingly consistent with what we see. But there's a catch. The simulation shows that even a shattered core should eventually settle back down into a solid ball. Yet, billions of years later, Jupiter remains fuzzy, refusing to obey the simple logic of gravity and sedimentation. This leads us to a startling realization. We don't just misunderstand Jupiter's anatomy, we misunderstand its very nature. If Jupiter is a liquid metal world with a dissolved heart, it acts more like a giant, churning engine than a rock. The heat flowing from its interior is actually greater than the heat it receives from the distant, dimming sun. Jupiter is essentially glowing in the dark, radiating its own internal energy out into the cold reaches of the outer solar system. This internal furnace is what drives the massive weather patterns and the 1,000-year-old storms that we see on the surface. It is a world where the weather is dictated not by the sun above, but by the crushing metal oceans far below. Every time we think we have a handle on this giant, it reveals a layer of complexity that humbles our best scientists. We are forced to ask, if the largest planet in our system is this strange, what does that say about the rest? Is Saturn also a liquid metal world with a fuzzy heart, or is Jupiter a unique survivor of a chaotic past? To find the answer, we must look past the colorful clouds and accept that the universe is far less solid than we thought. The story of Jupiter is a reminder that the universe doesn't always provide the neat, solid answers we crave. We wanted a rocky core, a simple surface, and a predictable giant. Instead, we found a world of liquid metal. It is a place where hydrogen acts like a mirror, reflecting our own ignorance back at us in beautiful, swirling colors. This planet challenges the very way we categorize the worlds around us. Is it a planet, a failed star, or something else? Perhaps Jupiter is simply a bridge, a transitional step between the small rocky homes like Earth and the massive suns. As we continue to study the data from Juno and the missions that follow, the fuzzy core remains a haunting riddle. Was it a collision, a unique birth, or is the physics of extreme pressure simply stranger than we can currently calculate? We must learn to be comfortable with this uncertainty, for it is the fuel that drives our desire to explore. Looking at Jupiter is like looking into a deep, dark well. The further down you peer, the more of yourself you see. It reminds us that we are tiny observers on a very unique, very solid rock, floating in a sea of liquid titans. If Jupiter can hide an ocean of metal and a dissolving heart, what other wonders are waiting in the dark? The moons of Jupiter, Io, Europa, Ganymede, and Callisto each hold their own secrets, from volcanic fire to hidden icy oceans. They are small worlds dancing around a king that is constantly radiating heat and magnetic fury into their very foundations. Our journey into the solar system is just beginning, and our first major lesson is one of profound, beautiful humility. We aren't just living in a neighborhood of planets, we are living in a complex, energetic machine that we barely understand. Every new photograph and every new measurement is a small light being turned on in a massive, dark mansion. Eventually, we will understand how the fuzzy core came to be, and in doing so, we will understand our own origins. Until then, the giant will continue to spin, its metallic heart churning, its storms raging, and its secrets tucked away. So, the next time you look up at that bright, steady light in the night sky, remember what lies beneath. Jupiter isn't just what you think. It is a magnificent, liquid mystery waiting for us to finally find the key.